Okay, part 3, we're almost done. So at the end of part 2, I got to this point where I said, hey, let's multiply row 3 by a 2. And I don't care what happens here. I don't care what happens here. I don't really care what happens here. My goal is to, just like I did on the first one, is to get rid of the z's. Remember when I added this z to that z? They canceled. So now, I'm going to do this in my head. This times this. So I forgot that we already had one equation. After we added 1 to 3, this is what got spit out. So now we're going to manipulate 2 and 3. This times this plus this is 7. This times this is negative 2z plus 2z is gone. This times this is negative 8y plus this is negative 7y. This times this is 2x plus negative 2x is 0x. Now, I didn't intentionally make that happen. It just happened. So it's like a gift. If this doesn't happen, you've done what you're supposed to do, but typically this doesn't produce a 0x. It just did. So you'd have to treat this just like we practiced in class, where you have to use elimination or substitution to solve this system. Much easier system to deal with. But because this was a gift, we're going to take it, because it's actually negative 7y equals 7. Divide by negative 7, divide by negative 7. I get negative 1 is my y. So I know that goes in the middle. Now I got to go on the hunt for x and z. Well, I'm going to put this in right here. So I get 2x minus 3 times negative 1 equals 11. So 2x plus 3 equals 11. I'm going to subtract 3 from both sides. 2x is 8. So divide by 2, I get x is 4. Now I know x. Now I know y. I got to find z. Well, I can pick the first one, second one, or third one. The first one looks awfully easy. So x comes first. That's 4. Plus y is negative 1. Plus z is 9. So that's 5. Whoopsie. Simple math. 3 plus z equals 9. Subtract 3 from both sides. I get z is 6. There's my final piece. Last two, sigma notation. Looks fancy. Really isn't. So I'd hate for this to pop up on an ACT, SAT, and you just have no idea what to do, when actually it's kind of simple. So this is just saying let n go from 1 to 4. So that's just saying let n be 1, let n be 2, let n be 3, let n be 4, and calculate them for all of these. So f of 1 would equal 3 plus 2 times 1, which is 5. Put a 2 in there because of this. 3 plus 2 times 2. You can see that's 3 plus 4, which is 7. You can see this is going up by 2. And so maybe we just say, aha. I mean, you can just see it's going to be a linear arithmetic sequence. 6 plus 3 is 9. And now you can just go, you know what? That's going to be 11. Add them up. 12, 21, 33. Now, we get to a problem like this, and it's not so straightforward. We're like, wait a minute, we got that formula, the sum of each element in this arithmetic sequence. And it's going to be our buddy. So we can see that we have 14 of these. And yes, we could use that technique, but we don't want to do that. So the sum of the all 14 elements, if I was to do this long method, would be 14, because that's the number that we need there, the final one. And we got to know what the first one is, so we do have to plug in f of 1. So n equals 1, that's the first one. We're going to plug it in here. We get 3 times 1 minus 1, and that's 2. But we also need to know the final value, or the final number in our element, which for this one was 11. But this one, we're going to have to put in a 14. 14 times 3 is 42, minus 1 is 41. So if we plug this in, we're going to put a 2 plus 41 all over 2. Clean this up a little bit. 14 times 43 over 2. The way I like to do it is just clean stuff up that can be cleaned up. So that's 7. 7 times 40 is 280. 7 times 3 is 21. So that'd be 301. And that does it, you guys.